Thank you, and good afternoon. I would like to thank the symposium organizing committee for this opportunity to present our research at the Sustainability in Ship Design and Operation Conference. Today, I will discuss our research on magnetically recoverable nanocomposites for treating vessel discharge. Our goal is to develop cost-effective, eco-friendly, usable, and highly functional nanocomposites for treating vessel discharges using magnetic separation technology. A nanocomposite is a multi-phase solid with at least one phase being nanoscaled. At the nanoscale, materials exhibit spatial and size-dependent properties, making them extremely fascinating. Nanocomposites represent an exciting class of advanced materials due to their synergistic properties derived from their components. Natural nanocomposites are widespread. Examples include hard and tough bones, teeth, seashells that are built of alternating nano layers of hard inorganic minerals and soft, stress-dissipating organic polymers. Nanocomposites offer unparalleled properties unattainable with conventional materials. Shipping plays a vital role to the world's economy, transporting 90% of the food, products, and energy worldwide. In the United States, it contributes to $650 billion of the GDP, and there is a growing demand for waterway transportation. However, vessel operations generate substantial wastewater, including bilge water, ballast water, and deck runoff. Bilge water contains various oils, while ballast water, used for stability, can introduce invasive organisms to new marine environments. These discharges are major sources of pollutants such as oil, grease, invasive living organisms, pathogens, and harmful chemicals like suspended solids and heavy metals. It was not until about 50 years ago the International Maritime Organization, or IMO, recognized the need to protect the marine environment and established the international regulations. The key document, MARPOL 73 and 78, enforces stringent limits on vessel discharges. Ballast water pollution came under regulation in 2017 with limits nearly at zero. Violations may result in substantial penalties or imprisonment. Current water treatment employs combined chemical, physical, and biological methods to remove pollutants, including reducing oil content to less than 15 parts per million, or ppm. Examples include filtration, flocculation, ion exchanging, and gravity separation. But no matter which types of wastewater, before discharge, disinfection is necessary to meet the MARPOL regulations. Two main disinfection methods are traditional chlorination and the newly approved UV radiation treatment. Chlorination is corrosive and generates cancer-causing byproducts, while UV radiation is expensive and requires particle-free water. Moreover, certain microbes can withstand UV radiation or reactivate after discharge. In recent years, we have developed several magnetic-based nanocomposites for water treatment. This includes a high performance magnetic polydimethylsiloxane nanocomposite sponges for oily water separation and titanium dioxide-based magnetic nanocomposites for water disinfection. Shown here is an example of our magnetic nanocomposite products. As you can see, these products enable rapid recovery for potential reuse and the secondary pollution elimination through magnetic force. They offer instant, controllable, and non-contact actions that are not affected by rough sea conditions. Most of them incorporate magnetite nanoparticles for their superior magnetic properties, combined with other components to achieve specific structures and functionalities. Today, I will discuss our development of silver nanoparticle-based magnetic nanocomposites for water disinfection. Silver nanoparticles demonstrate potent antimicrobial effects against the bacterial, fungi, algae, and the viruses at very low concentrations with minimal sensitivity to contaminants. We believe silver nanoparticle-based nanocomposites are the most practical and promising antimicrobial agents for water disinfection. However, the EPA recommends less than a 0.1 ppm level of silver in drinking water. And many reported silver nanoparticles based on antimicrobial agents release silver at levels 5 to 100 times higher. Our initial effort involved incorporating silver nanoparticles and the magnetite nanoparticles onto an activated carbon matrix, which we've termed MAC-AG. Our MAC-AG product proved highly effective for water disinfection. For instance, 0.5 grams of MAC-AG containing 0.15% silver was shown to kill 2 × 10⁶ colony forming units, or CFU, in just 15 minutes. A sample with 0.22% silver was shown to remove all 10⁵ viable microbes from Long Island Sound surface water within 3 minutes. However, we noticed that after multiple repeated uses, the nanocomposites became less responsive to magnetic field, significantly decreasing their recovery rate. This was attributed to the oxidation of the iron 2 ions by dissolved oxygen in water to the much less magnetic iron 3 oxide. Additionally, for silver content greater than 0.22%, atomic absorption, or AA spectroscopy, suggested a potential silver release above 0.1 ppm. Both are big issues concerning the product's reusability. To address the first concern, we enhanced the magnetite's stability against the oxidation by coating magnetite nanoparticles with a silica layer, forming MS nanoparticles. Unlike typical stable method using tetroethoxysilane, or TEOS, as the silica source, ammonia, varied alcohols as solvents and binding agents, often at elevated temperatures, we introduced a greatly simplified and green approach. For the first time, we utilized the water as the sole solvent in the stowable process to achieve silica coating on magnetite nanoparticles under ambient conditions, eliminating the need for alcohols or stabilizers. The transmission electron microscope or TEM images on the left display the as prepared MS nanoparticles, showing an uniform ultra-thin silica coating about 2 nanometers thick. The magnetic behavior, as shown in the right figure, indicated both the control and the silica-coated magnetite nanoparticles exhibited superparamagnetic properties, becoming highly magnetic in the presence of an external magnetic field and non-magnetic as soon as the field was removed. MS nanoparticles also displayed a very high magnetization of 59 EMU per gram. In the middle figure, accelerated oxidation tests revealed that while magnetite nanoparticles became unresponsive to the magnetic field after just 1 minute of sonication in water, MS remained very responsive even after 5 days of sonication. The high magnetization and the oxidation stability were also shown to extend to products with added components and functionalities. Our approach offers substantial advantages in terms of simplicity, safety, material cost, and reduced environmental impact compared to the conventional stowable method. After this, we bonded the silver nanoparticles to MS, forming MS-Ag by reducing silver ions attached to MS with glucose to address the second concern, that is preventing excess silver from leaking into the water. We introduced a novel approach. For the first time, we encapsulated MS-Ag with an outer mesoporous silica shell, creating the core multi-shell nanocomposite referred to as MS-Ag meso-S. This was achieved by extending the cation C-type micelle templating strategy with a modified Stauber method. In this process, we used the C-type or acetyl-trimethyl ammonia bromide as the pore-forming template surfactant. In water, C-type molecules, about 2 nanometers in length, self-assemble into micelles. These micelles, along with the silica oligomers, subsequently and cooperatively assembled onto the surface of MS-Ag particles. This assembly resulted in these cylindrical C-type micelles, extending outward and surrounded by silica oligomers. Further condensation of silica oligomers formed silica walls between C-type micellar channels. The later removal of C-type molecules in ethanol produced the mesoporous silica outer shell. In our initial proof of concept work, we used the ammonia as the base catalyst, as is common in the Stauber method. The resultant nanocomposite was labeled ammonia 7.5, with 7.5 representing the use of 7.5 milliliters of silica precursor, TEOS. Later, due to concerns that ammonia might etch the coated silver away because of its complexation with silver ions, we switched to sodium hydroxide as the catalyst. With sodium hydroxide, we varied the amount of TEOS to explore the control over channel length and the silver release rate, producing nanocomposites named sodium hydroxide 1 through 7.5, where the number indicates the TEOS used. The BET surface analysis along with the TEM images confirmed our successful formation of mesoporous silica shells on MSAG. The left figure here displays the pore size distributions of the nanocomposites based on the BET analysis. It can be seen sodium hydroxide catalyzed samples demonstrate very narrow pore size distributions with a sharp uptake at 3.9 nanometers. This agreed excellently well with the expected about 4 nanometer mesopore sizes templated using the about 2 nanometer long C-type molecules. Compared to mesopores in literature methods, which ranged at least 60 nanometer with broad pore size variations, C-type templated mesopores were much smaller and much more uniform. This corresponded to significantly enhanced surface structural regularity or smoothness at the nanoscale. TEM inside images of sodium hydroxide 7.5 and ammonia 7.5 revealed similar porosity and structure, regardless of the catalyst used. In both cases, uniform pores about 4 nanometers in diameter, separated by silica walls about 2 nanometers thick, were observed. The mesopore cell thickness was also found to be influenced by the amount of TEOS, increasing from approximately 10 nanometers to 80 nanometers as the TEOS amount rose from 1 to 7.5 milliliters. Energy dispersive spectroscopy or EDS elemental maps of the nanocomposites confirmed the presence of all expected elements, iron, oxygen, silicon, and silver, which all shared the same spatial distributions. The fact that where silver was found, all other elements were present confirmed that silver nanoparticles were truly incorporated in the final products. The zones of inhibition test clearly indicates varying antimicrobial capabilities among the samples when placed on the E. coli culture. MS shows no antimicrobial activity, while MSAG demonstrates the greatest ability to inhibit bacterial growth. As expected, ammonia 7.5 exhibits lower inhibition compared to MSAG, attributed to the outer silica coating with mesoporous channels. In the figure on the right, the inhibition zone diameter decreased linearly with increasing TEOS amount without any added TEOS. MSAG shows the largest inhibition zone diameter at 5.4 millimeters, allowing silver ions to readily inhibit E. coli growth. The addition of 1 milliliter of TEOS generated a 10 nanometer thick mesoporous silica shell, reducing the diameter to 4.6 millimeters by increasing the path length for silver ions to travel out of the cell. When 7.5 milliliters of TEOS was used, the shell thickness increased to about 80 nanometers, and the inhibition zone became hardly visible. This demonstrated the tonability of mesopore, the mesoporous shells for controlled silver release. All of this reaffirms the critical role of silver in the biocidal activity of the nanocomposites. We once again demonstrated the varying antimicrobial capabilities of the samples by treating E. coli cultures with counts ranging from 10 to the 4th to 10 to the 6th CFU per ml, utilizing a shaking method. Each 5 milligram sample was introduced to 1 milliliter of culture, with sampling occurring every 3 minutes. In the left side figure, MS showed no change in bacterial count after 15 minutes of treatment as expected. MS-AG eradicated all bacteria within 3 minutes, while not as rapid as MS-AG. Ammonia 7.5 demonstrated an excellent antimicrobial efficacy, reducing bacterial count with increasing treatment time. To assess sample reusability, we repeated a 15-minute treatment on various cultures 3 times. The nanocomposites disinfection abilities remained unchanged throughout the 3 cycles, as depicted in the typical play results shown here. We investigated the leaching of silver ions into water from MS-AG and ammonia 7.5 during 6 repeated shaking cycles, each corresponding to a 4-log rhythm reduction in variable E. coli counts. The silver content in each supernatant was determined by AA spectroscopy with a detection limit of 1.5 parts per billion. Figures B and C reveal that for all ammonia 7.5 samples across the 6 cycles, the silver release levels remained remarkably constant and very low, at levels below 0.015 ppm, regardless of disinfectant amounts and varying temperatures. These values, confirmed by ICP mass spectrometry, were significantly lower than the EPA's 0.1 ppm recommendation. In contrast, as shown in figure A, all MS-AG samples showed silver releases above the 0.1 ppm EPA recommendation level. The remarkable biocidal efficacy with minimum silver leaching can be ascribed to the nanocomposites mesoporous silica shell surface, characterized by hydroxyl groups and a high degree of structural periodicity at the nanoscale or smoothness. These features promote close association with bacterial and facilitate high local silver ion concentrations at the nanocomposite solution and the bacterial interfaces where biocidal actions take place. The feasibility of applying the nanocomposites for disinfecting Long Island Sound surface water was also investigated. Long Island Sound surface water samples were collected and treated with 1 milligram per ml of ammonia 7.5 and sodium hydroxide 2 nanocomposites. The play results presented here confirm the absence of viable microbes in these water samples after 20 minutes of treatment. While our previously reported MAC-AG nanocomposite achieved similar antimicrobial results, the mesoporous nanoplatforms significantly reduced the silver leaching by a factor of 10 to 1,000. Here we propose an advanced ballast water treatment system utilizing silver nanocomposite for effective disinfection. Cargo ships typically hold 1,500 to 5,000 cubic meters of ballast water during international voyages lasting 20 to 45 days. In this example, the system disinfects 6,000 cubic meters of ballast water, achieving greater than 99.99% microbe eradication in just 5 days, requiring 5 compact silver treatment units. Each unit sized at 5 cubic meters contains 25 kilograms of silver nanocomposite for optimal performance. This system minimizes silver leaching into treated water, which may sustain disinfection during the voyage and can be recovered before discharge if necessary. Further research and the prototype construction are planned for our future work. In summary, the magnetic functional nanocomposites developed in our lab are shown to be highly synergistic with remarkable performance. They're easy to prepare, readily recoverable, reusable, and structurally stable and tunable. All of this make them green, low cost, thus excellent candidates for treating vessel discharges, including disinfecting ballast water. With that, I would like to thank the U.S. MMA Dean's Office and the Brookhaven National Laboratory for their generous support in funding and providing research facilities, and the following individuals whose invaluable contributions not only ensured the success of the project, but also made the journey fun and memorable. These individuals are my research students, Alex Furlan, Adam Fisher, Monica Keeley, and my colleagues, Kim Kieslinger, Mike Melser, Dimitra Naki-Penchuk, Brian Ackerman, Sergio Paredes, David Shane, and Anthony Nigro. I thank you all for joining me today, and we'll be happy to take any questions you may have. Thank you.
Yes,
Here,
please go.
Possible if we have some more explanation for the excellent brand implementation, what would the separation look like?
Could you hear that, Pete?
could you repeat the question? I'm unable to hear it clearly.
Sure.
Sorry.
The gentleman wanted to know what would a practical application of what you're proposing look like on board a ship? Right?
Would it treat all liquids at the same time, or
Would it be able to treat all kinds of pollutants or species at a time? Would it serve for everything?
Disinfecting silver is potent against all different types of microbes. So, you know, in terms of disinfection, yes, it's tackling all microbes, yes, including pathogens, but bacteria, algae, all these things causing biofouling. That's a big issue. UV light, right? It's unable to prevent biofouling, and it needs to be cleaned. Needs to be cleaned often, right? And here silver is in particular good against all this biofouling and algae growth, etc. as well. So that's one of our proposed use. It can also be used to disinfect drinking water on board ship. The same concept.
So how about, what would the practical application look like? I guess this would, the wastewater would have to be run through. Well, what would it look like? Would you drop these nanoparticles in there and then later just take them out with magnetic force? Or?
Are you able to see the screen I'm sharing?
Yeah.
Yes.
Okay, so this is a proposed application to treat ballast water. Okay, so this water coming through sea chest first, we'll go through this filtration unit to remove all those larger particles. Then they get to flow into the ballast tank here, and this water is flowing into the back units. So we have this silver disinfection or silver-based treatment units in the back. We have 5 of them here proposed. And so in each unit, so you have these nanocomposites that is used to treat the water. Once that is done, this water is going to flow back to the tank here. But you see the tank is separated into 2 compartments. The one part is treated water, another part is yet to be treated water. So, you know, and definitely more work is required to turn this into reality. So, but that is one possible application, practical application. These units are used to eradicate all these microorganisms in the ballast water before they're discharged back into ocean. You know, how many units you need depends on how much water you wanted to treat. You wanted to treat, right? Here we're assuming treating 6,000 meter cube ballast water. And this will require also 5 units of treating them for 5 days, achieving this very high, more than 99.99% material removing rate, killing rate, with very, very nearly, you know, very minimum amount of silver leach, because all these silvers are essentially recovered after each treatment through magnetic force. And this nanocomposites in each unit, it can be reused over and over.
Well,
And this
we
also
have-
can, yeah.
Thank you for the excellent presentation. After solving the corrosion problem with the iron and the silicon coating, what is the limiting factor of the lifespan on the nanoparticles themselves?
I couldn't
we-
hear very,
Why don't you come up here?
sorry.
Thank you for the excellent presentation. After solving the corrosion issue with the silicon coating, what is the limiting lifespan factor of the nanocomposites?
We really didn't follow the lifespan study. We didn't conduct a lifespan study for months, for years at this point yet. But we repeated the treatment or the cycles or repeated the uses for up to 10 times. We have seen no change in terms of its structural integrity, in terms of its performance or disinfection ability. We see no changes after 15 repeated uses. So lifetime, so the storage usually is the oxidation, right? Is the oxidation of the iron oxide, but it's well, you know, protected. We use this accelerated oxidation test through sonication. So after we sonicate the coated particles for 5 days, we see no change in terms of its structures, in terms of its performance. While the unprotected, uncoated magnetite nanoparticles couldn't sustain like 1 minute sonication, and that is the big change. And that's one thing. And our our silicon coating is very stable. We made sure during the synthesis we allowed it to really mature, or the condensation really goes to completion to form this polymer network that is stable. And based on literature search, you know, for the system that they undergo less time of this kind of condensation process, they see no changes over months, over 6 months, in terms of their performance, in terms of their properties. So we believe our life lifespan is very long as well. So we did take all that into consideration, how stable our system is, and we believe it's stable for a long time. And some studies, they didn't even go through as rigorous process as we did. They proved that their lifetimes can extend to 3 years without seeing any sign of deterioration or degradation, or yeah. So I think
you.
they're very stable. Thank you.
Thank you.
Okay, thank you very much. So we're going to, thank you very much.
Okay, so I'm gonna unshare my screen. Thank you.